Okay, this is a third lecture of the theory of machines, or linkage design and analysis, if you like. And well, I just wanted to start this lecture by a couple of examples still on degrees of freedom. And I have this linkage here in front of you, and I wanted to calculate the number of degrees of freedom of the linkage. And so that's like an example one. Let's say I have here how many links I have. I have 6 because they are already counted for us here, right? So and my revolute joints, I have how many revolute joints? That's an R, an R, an R, an R. So I have 4 revolute joints. Prismatic joints B2. So because simply this here is a prismatic joint and this is a prismatic joint as well. I have higher pair here. So that's a higher pair I have here, right? This connection, right? So when I calculate degrees of freedom, I go F is equal to 3 n minus 1 minus 2 times R minus 2 times P minus H. So 3 times 6 minus 1 minus 2 times 4 minus 2 times 2 minus 1 H. So this here is 15 minus 13, and then will be 2. So I have a 2 degree of freedom system here. So 2 degree of freedom, which tells me that 2 motors are needed, right? Then those 2 motors, where am I going to fit them? Well, I imagine one of the motors will be here. So that's motor 1. And the second motor would be possibly at the other end, like a linear actuator here. So this is motor 2. So this will be a linear actuator moving link 6 up and down. So together with the rotational motion of link number 2, the linear motion of link number 6 can give me, like, can cause the slider here, point E, to follow a trajectory of my choosing, type thing. And you know how the trajectory X and Y, 2 degrees of freedom values. So I need 2 degrees of freedom arrangement to be able to achieve that. So that's a possibility. And you can think about it also from the point of view if you decide to ground link number 6. So make this ground and calculate again, and you'll end up with degrees of freedom being 1. All right, so the linkage will still function. Grounding link number 6 is equivalent to just locking up the motor number 2. So locking this motor so it doesn't move, and you can lock the motor at different positions. So you can fix link number 6 at different positions, ground it at different positions, and every time you get different linear motion for link E, which is a slider. We will slide left and right, yes, but will have different particulars, if you like, depending on how high or how low you decide to fix link number 6. So the possibility that you are fixing, you can control the position of link number 6 means really 2 degree of freedom, because link number 6 together with link number 2 need to be controlled independently. So hence the number 2 here, 2 degree of freedom, makes sense to me. Now let's have a look at another example. And I have here a flight simulator, if you like, or a steward platform with a ground. So that's a ground here, and that's a platform or a table. I have 6 legs, right? I have 6 legs, and so every leg is really controlled by a linear actuator. like that's a linear actuator, or it can be a hydraulic or pneumatic cylinder if you like, similar to the linear actuator I suggested to this linkage here, link number 6, right? So it gives me a linear motion. Now, in this specific case, my question to you is whether I should allow the pistons to rotate inside the cylinders. Like, should I allow this piston inside the cylinders to rotate like that inside the cylinders, or just lock up this rotational motion? If I look up the rotational motion, I'm going to pay more money, by the way, for the design. But let's say I want to discuss this with you from the kinematic point of view more than anything. Right, so let's take it. Let's calculate the degrees of freedom if the pistons are not allowed to rotate. So that's case 1. Pistons are not allowed to rotate. Right. So now let's calculate degrees of freedom. Now, how many links I have in total? For every leg, I have, let's count the number of links per leg. So this link here at the bottom end, this is link number, I can say 1. Let's call it 1. But you know how I always preserve 1 for the ground, but I'm just counting the links on a leg, right? And the cylinder here is link number 2, and the piston is link number 3, and this other link at the very top here is link number 4. So this link here is link number 4, and it's allowed to swing, right? And as exactly like link number 1, that's allowed to swing right and left, okay, sort of thing. So I have 4 links per leg plus a ground plus a platform. So I have number of links. I have legs equal 6. So my number of links is 4 times 6 plus ground, 1 for ground, and plus 1 for platform, and they add up to 26. Okay, so I have 26 legs in this case, right? Now, how many revolute joints I have? So let's count them quickly. This was one revolute joint. That's another one. That's another one here. Correct? So I have, and there is this one here at the top. So I have per leg, I have 4 revolute joints, right? So R is equal to 4 times 6 legs, so that's 24. And now I have prismatic, I have 1 times 6 legs, so that's because this is a prismatic, because I assumed there is no rotation allowed. So that's all what I have in terms of joints and links. I can calculate my degrees of freedom. At the moment I go just now, F is equal to 6 n minus 1, because now I use 6 instead of 3, because that's 100% a 3D application or special application, minus 5 times R, minus 5 times P, minus 4 times C, minus 3G minus H, and I don't have those ones at the moment. I have those ones here. So I go 6, 26 links minus 1, minus 5 times 24, minus 5 times 6 prismatic joints. So in this case, F is equal to 23, 24. So in this case, F is equal to 0. Okay, so that's 0 here, right? Okay, meaning that if I don't allow the pistons to rotate inside the cylinders, this linkage is not going to move. Will cease type thing. So case 2, if I allow this motion to happen. So case 2, pistons rotate inside cylinders. In this case, what will be the difference between the two assumptions in terms of calculations? Difference now is, instead of this being a prismatic joint here, it will be a cylindrical joint, right? Because now the piston can, so instead of, so there's a piston inside the cylinder here, right? Let's say it's something like that, right? So now now currently it can only do that because it's not allowed to rotate. But when I add the allowance for rotation, it's that, right? So now I have a cylindrical joint. So this means P becomes C. So the equation will be F being equal to 6 times 26 minus 1 minus 5 times 24 revolute joints, right? That's in, minus 4 times 6, right? Or being C now. So this will give me 6 degrees of freedom, right? So now at this, with these calculations, now we can tell that the platform is going to be okay. We'll have 6 degrees of freedom, so we'll be able to place it and orientate it with 6 degrees of freedom. And because you have allowed the pistons to rotate inside the cylinders. In fact, if the pistons are not allowed to rotate, if I have a design of hydraulic cylinder, let's assume that the design of hydraulic cylinder doesn't allow this rotation to take place, I would have provided this rotation myself by possibly adding at the clevis end at the top here, adding a revolute joint or something like that, you see. But it's already if it's already provided, if the cylinder design would allow this, this will cover, will just give me this extra freedom. That will be useful, right? So now, by the way, when you control the platform, your 6 degrees of freedom are the 6 motions that provided by those actuators here, and it's quite like the calculations here quite complex because like if you want to place the platform at a given position orientation, you need to calculate all those 6 motions which correspond to this position orientation, and then you start moving those linear actuators to produce this like 6 motions for you, and then place the platform at a given position orientation. So that's a control problem also more than anything, because you need to be able to control the motion of those cylinders in such a way that they move accurately to the desired position orientation, and also to be quick enough so it give you the same feeling as if you are flying an aeroplane or something. Now, the new topic, the thing I want to talk about here is the 4-body chain. I want to discuss the 4-body chain, right? All right. So now a 4-body chain is simply just this linkage, which we have drawn a number of times before, and has 4 links and 4 revolute joints. So I have R, 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 and I have link number 2, link number 1, link number 3, link number 4. Hence, it's a 4-body chain, and people have been studying this for hundreds of years in terms of whether, like, if you put together a 4-body chain and you select dimensions, normally my dimensions here, that will be R2, R1, R3, R4, whether you'll be able to realize the possibility of having at least one link doing 360 degrees, because it's not always the case. And if you want this to be the case, then you have to design, like select the dimensions carefully, right? Sort of thing. Now, if one of the links is capable of doing 360 rotation, then we refer to the linkage as a Grashof, right? So Grashof linkage. This means one link can do 360 rotation. I can do full rotations. So whether you like when you select or you decide on the dimensions of R1 to R4, then you are not sure that your linkage is going to be Grashof or not. So if you need 360 rotation, then you need to apply Grashof rule, and you need to make sure that the links comply with the Grashof rule, so or Grashof law. So Grashof law is like that. Grashof law says S plus L should be equal to or less than or equal to. You see, and this equal to, I put equal to here in red because for a purpose. Like I want to talk about this later on, because always less than is what I want to achieve, and equal to is just on the borderline, and I don't want my linkage to be a borderline linkage. Okay, so the equation says S plus 2 should be equal to P plus Q. This is Grashof law, and if the linkage for bar linkage comply with Grashof law, then one of the links is going to do 360. At least one of the links is going to do 360, right? So, and this is the condition, right? This is the condition that one of the links is going to be 360. So what's LS then? S means the shortest link. So shortest link, right? Can be any one of the links, and this is the longest link. Longest link, and then those are the other two links, the ones that fall in between S and L, right? So, for example, just like a simple trivial example here, I'm going to say, just the example 3, I think. So, example number 3, I'm going to say if R1 is 50, R2 is 20, R3 is 70, right? And R4 is 60, right? Then is this a Grashof, right? The question is this a Grashof linkage? I'm asking you now. So now, and you go, all right, so it's really simple. The check is very simple. The shortest is 20, the longest is 70, right? And the other two are 50. P and Q, 50 and 60. I don't know which one is P, which one is Q, and it doesn't matter at all. Just anyone is, sort of thing. But really S should be defined and L should be defined. The other two are not important. That's why I didn't say P was 50 or 60 or whatever. Just the other two, and that's what matters to us. So I have now 20 plus 70 on one side, the other two 50 plus 60, and that's here, so that's okay. So my linkage is going to be a garage of one. Is going to do one of the links is going to do 360. Now, if one of the links is going to do 360, which link is going to do 360? Yes, if one of the links is going to do 360, it will have to be, see, this is the answer. It will have to be S if it was free to rotate. Okay, here, that's it. So if S is free, it will be the one that will do 360. All right, so if the linkage is Grashof, one link is rotate, this link is S if free, right? If it's not free, then two links will do 360. So let me just give you like some more details on this. So this will be different cases, if you like. We call them different inversions, right? So we call them inversions of the Grashof 4-bar chain, right? Those inversions, or inversions means cases, okay? Now, one of them is the most famous one, right? S is the one next to the ground, right? This one here, S is attached to the ground, right? So what will happen as agreed? This S is going to do 360, right? So it's going to do 360 rotations, and because it's a Grashof linkage, right? Okay, so now, and the other link at the other end is going to rock, will do rocking motion. So this will do 360 rotation, that's complete rotations, and this will do rocking motion, right? So we refer to this as the crank rocker linkage. So this here is going to be called the crank. So this is the crank, right? And this is the rocker, and this one in between will couple them together. We refer to this as the coupler. So that's my first arrangement here. That's R1. It might later on I'll call, R1, R2, R3. That's will always I refer to those links by these dimensions, and R2, R1, R2, R3, R4. Right. So that's one inversion. Okay. So now the other inversion is if S is opposite R1. So now I have the other case is this. So now that's R1, and that's a linkage. That's another linkage, and maybe I should give myself some room. So just a little bit here. So okay. So this is R1, R2, and R4 on the other end, and this here will be S. So that's S. The shortest link is here. That's S, right? So this is inversion number 2. Here, S is opposite ground. So what will happen? The promise was that this S is going to do 360, right? So in fact, you'll find that S will still do 360 as the links move. So those other, like here, I have those links will both rock. So I have two rockers. So rocker 1, right? And here rocker 2, and S will do 360, right? So somehow during the rocking motion of the two links, you'll find that S will be able to rotate, to do 360 rotation. So I have, in this case, I call this the double rocker inversion. S does 360. Okay, 360 degrees still, right? Okay, so that's a second case. Now, so if S was free, was allowed to rotate, it will be the only link that's capable of doing 360 rotations. Whether it's next to the ground in this case, which is the most common application, and you get the crank rocker arrangement, and because in this case you attach S to like a continuously rotating motor or something, and then the other case, if S is opposite the ground, then it will be still will be the only one that will do 360 only link. The other links around it will be able to rock from right to left. While it's doing that, at some point in time they will intersect, whatever will happen, and then you'll be able to see that S is doing 360 without, it doesn't have a specific pivot anymore like it had before. That's why I didn't draw a circle around it, because it'd be quite complex to do it. So I decided just to leave it and just explain to you. It will be the only one that will do 360. Now, if S was not allowed to rotate, so I still have a Grashof arrangement, meaning that the the condition applies, so S plus L is still less than P plus Q, but S, the shortest link, is stationary. So in this case, I get a different arrangement. So in this case, that's S like that, and those are the other ones around it. So that's S. Okay, so I have, so S is grounded. Here, S is grounded, right? Then that's an interesting one, because in this case, what I'm going to do is to get both links here, those both sides will be capable of doing 360, right? So now both sides can do and will do 360, right? So I have, in fact, in this case, I have two cranks, right? So this is a double crank arrangement. So that's a double crank inversion, if you like. So, so now if S is grounded, you have a double crank inversion. All right. So those are the three conditions, if you like, or a four body chain, which is Grashof. So either S is next to the ground, the crank rocker, or crank rocker, or S is opposite the ground in double rocker, or I have S being grounded or stationary, then I have a double crank inversion. In this case, you'll find that it's like exactly like two gears, meshing two gears together, but the velocity, like so, you'll be able to drive one of those links with the motor or whatever, and then the other link will follow this motion, will do 360, and the velocity of the other link will change during the motion. But in any case, that's a double crank inversion. Of course, if the link is not, if the linkage is not Grashof, none of the links will do 360. You'll have rocking motion, all that, like, sort of thing. And also non-Grashof linkage does have its own application as well, right? So just like wiping whatever, like, sort of, you need this rocking motion, some application, and you drive it with a servo motor that does certain angle in each direction type thing, so it doesn't do continuous rotation, but it does also exist like a non-Grashof arrangement. Now, what if this is, I want to here look at the situation, the special case, if S plus L was equal to P plus Q. All right, so you see how I said less than is what is my preference, but equal to still gives you a Grashof. But it's, well, it's a special case, in fact, and normally you'll find that the arrangement, you get a singular linkage. For example, if I have like this case, right? This case here, so I have that, right? So this is equal, that's equal and parallel. At some point in time, you'll find that this point A will fall here, A prime, point B will fall here, prime. So the whole linkage, right? The whole linkage collapses to a straight line. So the whole linkage, right, collapses to a straight line. And during the motion, right? So during the motion. Now, this is a single situation I don't want to have in my design, just simply because it does not, like geometrically, at this point in time after that, it's quite possible that point A prime will keep moving in this direction, but point B prime will come back. Geometry will allow this to happen. It's quite possible this will happen. So this will be, and dimensions will allow this to happen. Or they may go together in the same manner as before, and you may get something like that, right? It's like two possibilities for the linkage, like it can take two different shapes, two different configurations. I'm not sure exactly which one it will take, and this will be dictated more or less by the forces inside the linkage, the forces acting on the linkage. So it's not just only geometry that's controlling the motion anymore, and hence the singularity, right? Type thing. So that's like you get a singular configuration, if you like, singular linkage, if you like. Hence, it's better if you do S plus L less than, and then you fall in the safe, if you like, assured, geometrically controlled type linkage. Now, if I wanted to take things to like, I want to take this specific case, which is the crank rocker, and talk about it a little bit more. The crank rocker, right, inversion, and talk about this a little bit more on other ones now, because that's an interesting one, and you would see more of those in applications. So now, if I have the crank rocker, I'll just try to have a circle here, that, and just imagine another circular arc here, just to prepare my drawing. That's quite difficult to do on the, the surface or the screen of a surface, because it's difficult to control those like the stylus type thing. All right, so now I have let me take here a color, what such as this one, and let's say possibly I have my crank here, my rocker at the other end, and I just connect them together like that. So this gives me a specific situation. So this is link number 2, R2, length R3 for the coupler, and the rocker R4. What will happen if this point has moved to another position? So let's get another color here. So if it moved to another position, and we did look at something like that before, I'll be able, with the length R3, draw a circular arc over here, with this being the center, and then this will give me the new position of point B. So this will be new B, and if I connect that, like connect the 2 points here, I get my new position for, or new configuration of my linkage as this point rotates, like moves from here to there. All right, okay, so you can tell what I want to find now is how far point B is going to go in this direction type thing, because we agreed this link R4 is actually 4 is a rocker, so a rock between two different positions. So I want to find the extreme position of this link, or some other authors call this stationary position, because it will go to this position, will stop momentarily before it starts coming back and rock to the other direction, to another extreme position in the other direction. So I want to find this stationary or extreme position on the right hand side. So now we realize now that as this angle increases, right, you'll find that point B is thrown away. So you'll find that point B will keep going away, further away, till this angle is 180. So you'll find that you get a situation such as this one. So you'll find point A, I'm going to call it A prime here, and this length here will be R3 type thing, and this will give me R4. So this is the prime. All right, so this will be my first extreme position. Right, now what happens if point A continues rotating? So if it continues rotating, let's say it comes to here. So if it's here, and you want to find where point B is going, so it's here. Then with the compass positioned at this point here, you can draw that, and you'll find that this will be a new position for point P. Okay, this was the new position for point P. So you'll find that this angle now, which was 180 previously, now it's going to be smaller and smaller and smaller. And every time you'll find that point B is moving backwards, like in this direction type thing, till the angle between the, like this angle here, becomes 0. The other extreme value was 180, now it's 0. So now I'll just try to draw this with a different color, different out of colors, but maybe I can use black again or something like that. Right, so this will be, right, so let's say it's here. So this will be now B dash dash, and this is A dash dash, like that. So now I'm saying, of course, here my drawing is not accurate, but like this distance should be R3, right? That's this distance here is R3. So this here, this means R3 is on top of R2 type situation. So now, okay. So now if I wanted, so I have now my two extreme positions of the linkage, because now this will be, I'll go back and just change the color again. Yeah. So this will be the new position of the linkage here. I just use it here, just so that. Okay. Now with the two extreme positions known at the moment, I can find some particulars of this linkage. So I can say here, like this angle here, the angle through which link 4 swings is the stroke of this link 4. So this is the stroke of link 4. So it's really angular stroke, if you like, is the stroke of link 4. We can give this some, we can say, for example, let's call it gamma or something like that. Okay, right, so this is the stroke of link 4. Now, by the way, I want to say to find point B2 before I get further into that, I can just place the compass here and draw this arc with R3 minus R2, right? Okay, and this arc here was R3 plus R2, right? To find the prime one. So the B prime and B double prime, those actually specify for me, signify for me the end motions of link number 4, right? Okay. So this is, and the stroke between the two, the angle between the 2 points, if you like, between R4, which the positions of R4, which correspond to those points, this angle is equal to gamma. This is a stroke. All right. Okay. So what happens now is I have my crank rotates between A prime and A double prime, right? To bring the crank, to bring the rocker from B prime to B double prime, okay? And then the crank rotates from A double prime to A prime to take the rocker back from B double prime to B prime. So now that's an interesting concept now, because if I say, so I have now, I'll call this angle phi, right? I'll call this angle phi. So this angle, so the crank rotates by an angle phi. Just write, take some notes here. Okay, a crank, right? Just crank rotates by an angle phi. So that's crank R2, right? Rotates by an angle phi to move the rocker, right, from to E, right, angle gamma, all right, and then the crank rotates, the crank, right, rotates by an angle 360 minus phi, so this here 360 minus phi, to take the rocker from B prime to B double prime, angle again equal gamma. All right, okay, so now this is my interesting argument here. So the rocker moves in each direction the same angle gamma, the stroke of the rocker, right, in each direction. Now but the crank has a different angle which matches or corresponds to each motion type thing. So you'll find that, so it's phi 4 gamma and 360 minus phi 4 gamma returning type thing. All right, okay. Now the crank usually rotates at a constant velocity. Okay, so omega 2 is always constant. Omega 2 is always constant. Omega 2, that's constant. So then, which means I have two different times here. I have a time which corresponds to phi motion. I have a different time which corresponds to 360 minus phi. So for phi motion, right, I have a time, let's say, let's call this t1. And for 360 minus phi, I have another time which is t2, right? Which one phi is greater than 360 minus phi. So then this means T1 is greater than T2. So T1 is greater than T2. What this tells me, it says that from point B double prime, this point here, to B prime, the rocker moves a distance gamma in a large time, but which is T1. But when it comes back from B prime to B double prime, it moves the same distance, but in a smaller time frame, which is T2. So it does it quicker. So this means the rocker moves in one direction slowly, the motion which corresponds to T1 with the angle phi, and moves in the other direction quickly. And this is where it returns from B prime to B double prime. So in this case, we have what we call a quick return motion. So the rocker moves from B double prime, right? That's here, to B prime slowly and from fast, right? So this here is what we refer to as, this is the quick return motion action. All right, so this is a quick return motion action. So now to find that the the rocker moves in one direction slow and then comes back quickly and so on. So same angle, right? Then the ratio of time, the time ratio between like the slow motion to the fast motion is called, referred to as the time ratio of the linkage. So, right, time ratio, normally we refer to it as Q, right? Q, which is phi over, I'm just, instead of saying phi over, I'm going to say initially it's really T high over like long over T short, which is phi over 360 minus phi. This is the time ratio of the linkage. Normally it should be greater or sometimes equal to 1 in some applications, but greater than 1. An application with a time ratio equal to 1 is this one here, right? No, I'm going to show you first an application with time ratio greater than 1, right? So example of a quick return motion. So now if I have here, if I have a linkage such as this one, right? So this is here, it's a revolute joint, and this is a slider. This link number 2, that's a revolute joint here, and this link rotates whatever, right? So link number 2, omega 2, find the time ratio of this linkage. Then how would you do that? Like you need to find the maximum throw. So if this linkage here is number 3 and this link number 4, So the link number 4 is a rocker, right? Link 4 is a rocker. 4 is going to rock between two positions, two extreme positions. We need to find the two extreme positions of link number 4. So as far as it will go on the right hand side, when it's tangent, right, and this angle will be 90 degrees. This is as far as it can go. And the other side also, when it is tangent to the other side, and this is 90 degrees as well. So this is this extreme position 1, extreme position 1, tangent. This one here is extreme position 2, which is also tangent, right? So the stroke then, this is a stroke. This is the stroke here, right? Or gamma or whatever you want to call it, right? Now I want to find my time ratio. Time ratio, which is a time for, so I have now slow stroke and a fast stroke. Which one is slow, which one is fast, right? So the stroke which corresponds to the large angle is the slow stroke, which is angle phi. So that's here, phi. That's a slow stroke. So I'd say this is here, slow stroke, right? And then the fast stroke is coming back, right? So here, that's fast stroke type thing. So, right. So in this case, then, so this is 360 minus phi. The stroke which corresponds to that is the quick stroke or fast stroke. Time ratio is equal to phi over 360 minus phi. Now, I want to say something here which is very important. I want to say that if you are doing some power, like doing some job or some work with the rocker, because normally the rocker will be attached to another link in a machine to do something, cut in a metal or do whatever. Then, so there will be a power stroke, and then which the power stroke during which this output link, like the rocker, will do the job, will exert some force on something or some torque on something, and then there will be a return stroke to start the cycle again, right? Usually the power stroke corresponds to the slow stroke, right? And then when it comes without any resistance, just to start a new cycle, because there's no force when it's coming back. I can bring it back quickly, type thing. So normally when it is doing a job, I do it slowly, and then when I come back quickly, type stuff to start a new one. So the power stroke corresponds to the slow stroke. Don't forget that. This is important. Okay, so this normally is an exam question, in which direction the power is done or the job is done, and you look at the direction of rotation and of the rocker or whatever, from right to left or left to right, and you say which direction corresponds to. You look at which direction corresponds to the slow motion, and you say it is the job is done from right to left or from left to right, based on the direction of rotations you have in the problem you're dealing with. So this was a very important aspect of linkage in general, which is the quick return action of the linkage. All right, just a simple example for like where the time ratio is 1 is this linkage here. Okay, so that's because over here this link moves on circular arc again, so it moves in a circle, and then here this is one extreme position, right? And then when it comes back, the second extreme position will be here, type thing. So this will be the stroke, and it's really 180 and 180, right? So it's really 180 coming back 180. So Q is equal to 1, right? So I wanted, because I promised to show you this specific example. Now, what if another interesting aspect of 4-bar chain is referred to as a mechanical advantage, because the linkage is really meant, normally the input velocity is large, velocity at the output link can be smaller, whatever, but the torque in return, input small torque, will be magnified to a high torque at the output end type thing. So because it's just like levers, like those mechanical levers, hence because we multiply the torque, magnify the torque, the linkage has a mechanical advantage. So this is one of the things you think about when you design a 4-bar chain. What is a mechanical advantage of this linkage? And then let's just see if I can draw a simple thing here just to explain my point. So right, so I'm going to say a mechanical advantage, normally just MA of a linkage, and my linkage is here. Okay, so now let's say I have a torque T2 and the resisting torque T4. Just assume that this will be force will be transmitted here. So F will just go right through that. So now if I want to calculate this force, I'd say, okay, maybe if I just, okay, just draw like 90 degree, will give me an arm A2, another arm A4, sorry, and then I can say maybe T2 is F times arm A2, and T4 is equal to F times also times A4. Now, if I say then T4 over T2 is equal to then A4 over A2. And this is a mechanical advantage, should be greater than 1, right? And then you can calculate mechanical advantage from just A if you like, or you can do some more geometric stuff just to calculate it like that. And say, if you say this angle here is angle alpha or whatever you want to call it, then you can say, because that's 90 degrees, you can say A2 is, you can say this length is L2, right? And this length here is L4. So you can say A2 is equal to L2 sine alpha, and A4 is equal to L4 sine alpha, the same angle alpha. Then you can say these are equal to L4 over L2, because sine alpha will cancel out, and hence because L4 is greater than L2, L4 is greater than L2, since then we gain mechanical advantage, right? Some mechanical advantage. So the linkage has a mechanical advantage to it, because it sort of amplifies the input torque before it transmits to the other end, and you expect this from a linkage, right? Just like more than a lever, set of levers arranged together than anything. Now I want to say here that those lengths L2 and L4, they are not, those dimensions are not fixed. Of course, they change with as the linkage moves. So you don't expect the mechanical advantage to be constant in the linkage. Of course, right? But when you design the linkage, design the mechanical advantage, like mechanical advantage against some single degree of freedom linkage. My input parameter would be possibly be this angle here, the angle of the input link, right here, this angle here. So it changed from 0 to whatever, from 0 to 360 or something like that. And mechanical advantage will be some value. And I want to make sure that the mechanical advantage will remain above certain value, right? Above a certain value. So that's, as a designer, you control the mechanical advantage. And let's say if you say this is the minimum value of mechanical advantage, this minimum value of mechanical advantage will be function of your, like, function of all, like R1, R2, R3, R4, and this sort of stuff. So you select the dimensions to give you certain mechanical advantage needed for a specific application, right? All right, so at least minimum mechanical advantage shouldn't fall beyond certain value. So that's one important aspect, or an index of merit of a four-body chain. Another index of merit of a four-body chain is referred to as a transmission angle. So another one is called the transmission angle, right? And just to understand that, that's very much related to mechanical advantage, right, in a way, because mechanical, let's say I have a four-bar linkage such as this one, right? Then again, I have my torque T2, my resistance torque T4, and I have my force here, and this force, as agreed, is equal to, this is A4, so the torque is the force times A4, the transmitted torque, correct? Okay, is equal to the force times, which travels through the coupler, times A4. Okay, it makes sense. Now, if this angle here is mu, this length is fixed, is R4, I can say it's F, and A4 is simply R4 sine mu, right? So here, this is the transmission angle, right? This is transmission angle here. So the idea here is I want sine mu to be as close to 1 as possible, because the maximum sine is sine 90, that's 1, right? So I want sine mu to be as close to 1 as possible, or we want mu to be as close to 90 as possible. Of course, it will not be close to, it will not be 90 or anything like that, but we want, it's just a design, something we want to achieve, want it to be as close to 90 degree as possible. Of course, mu is not constant as well, exactly like mechanical advantage. And then we'll look at maximum value and minimum value of mu, and we don't want the minimum value to fall far behind 90. I should say this is possibly what we want to achieve in a more accurate expression. We don't want mu minimum to fall far below pi over 2, right? Then you can find maximum minimum mu by just saying that. Okay, let's doing the following. So I have my linkage here, right? I know this is going to move on a circular arc, so that's circular arc here, and this will move also in a circular arc, right? So sort of thing. So like if this point A, point B, if this is A well, a note, okay, and then what will happen here is this is R3. I can draw R3 like that, and this will be R4. So when this is horizontal, when R2 falls or is like falls above R1, like on top of R1, I get mu minimum. So this is mu, the minimum value. And the other situation, when R2 is like that, and I get, this is R3, I get mu max. So those are the minimum and maximum value of mu. In this case, this distance here is R1 minus R2. In the other case, this distance here is R1 plus R2. In each case, I get a triangle. This one here is, if you like a small triangle. This one is a large triangle, and because mu minimum faces the side which is the smallest side, and here mu maximum faces the large side type stuff. So this is where you get maximum minimum mu, and you wanted really mu minimum to fall, not to fall far below pi over 2. That's like an index of merit, something you try to achieve when you design a 4-bar chain. So at this point in time, we come to the end of this lecture. And then from the next lecture, I hope we'll be looking at the geometric or position analysis, kinematic analysis of linkages. We'll explain what this means, and we'll start by position analysis of linkages. Please try to do as many problems as possible. Look at tutorials, and if you face any problems or something is not clear to you, contact me by a model or send me an email, and I'm happy to answer your questions. Good luck, and we'll see you again next time. Bye for now.